Thanks for having me today, and hi everyone. I'm Sam Green. I'm a co-founder and the head of research at Semiotic Labs, and today I'll be presenting on our work with using reinforcement learning for query pricing in the graph protocol. I'll first give an introduction to Semiotic Labs. I'll then cover automated price discovery, our automated price discovery work, and how we implemented and trained models for or agents for bidding in the graph. And then I will quickly show how our agents are working in production. Semiotic was founded in 2020 by AI and cryptography researchers. We've received funding from the National Science Foundation. We're in the US, the Graph Foundation, and Infinity Ventures. We're focused on applied research, and we are a core developer team of the Graph protocol, where we focus on AI and cryptography. And we are also the creators of Odos, which is a smart order router. Okay, so here's our scenario in the graph protocol. So at a high level, for those of you that don't know the graph, what we do in the graph is we index blockchain data, and we make it easy for people to query that blockchain data. And we're used primarily for dApp developers to build decentralized dApps. If you go, for example, if you go to Uniswap and you look at their price feed, and look at where the data is coming from, that's all coming from the graph, and we're used by most other major protocols for their data for their dApps. What happens in the back end is that we basically it's a two-sided market where we have customers they want to get queries, they want to get data, and we have indexers who index the blockchain data and serve it to the customers. And so what happens is we have this marketplace, a query market. It happens on this thing called the gateway. And customers, what they do is they'll send the queries that they want, GraphQL queries, and their GRT, which is the token they use for payment for queries, to the marketplace. And then indexers get to see what particular queries are coming in, and they will place bids in order to fill the queries. They don't get to see the actual budgets of the customers. That's a key point here. And of course, then the indexers receive the queries and they receive the payments for when they get to fill those queries. We have this talk is about a tool that we have been building, that we've deployed into production. It's called AutoAgora, and it does dynamic pricing based on the query volume received by an indexer. So we're using agent-based modeling. We used agent-based modeling during the development of AutoAgora. And if we look into the details of what's happening when we were doing development to build the models, we had a simulation environment that had a query distributor. It basically chose which agent got to fulfill or fill the query. And it also it has a traffic generator that simulates query volume. And then we have agents that can express bids in a domain-specific language called Agora. And that's why we call the system AutoAgora. Our agents are based on Gaussian bandits. These are a subtype of reinforcement learning. So they solve the exploitation problem. The bandits are very simple. They have two parameters, which they parameterize a Gaussian distribution. So this means basically these agents choose prices and they select prices from this distribution. And these are so this is what we use. So for example, here we have an agent that has sampled 0.8 for a price. And we see that it has a fairly tight distribution, which means that it's unlikely to select prices out of this area. And then we have another agent that is also interacting in the environment, and it's sampled a higher price. So some assumptions that we had for during training was that our query volume is parameterized by these two parameters. We have a query price that can be that will adjust dynamically, and we have query volume that will adjust dynamically. And so again, this is for development purposes, for training, or I'd say building the solution. And what this is doing is it's generating queries for the simulations for the agents to train against. And then if we look at what the goal of the agents the agent's goal is to maximize their revenue. So that's their objective, is to find prices that can win bids and fill the most queries and maximize the revenue. And on the other side, in the marketplace cares most about quality of service. They don't care about revenue maximization, or the marketplace doesn't care about revenue maximization. Okay, I'm going to give you one of our experiments that we did during development. We had a single agent placing a bid. The bid went into the marketplace. The marketplace, it was receiving simulated GraphQL queries and simulated budgets from a simulated indexer. And this is showing you some results from a trained agent that learned how to interact with that environment. So this experiment I'm showing you has a single agent. We've also done many experiments with multi-agent and multi-consumers. This has a single agent, single consumer. I'm going to show you a video in a moment, and I'd like to help you understand what that video is going to be showing. At the top, we will show a plot that visualizes the query volume, which is represented by this line, and a budget, which is represented by this line. So this line right here represents how much the consumer is willing to pay for their query. An important note is this amount is hidden from the indexers. So you can think of this as the indexers are trying to discover what the clearing price is in the marketplace. They don't know a priori. It's not given to them. And here, what you see with this dashed line is it's the initial policy, and that will stay fixed for the visualization. And the solid red line is the current policy. We then have the query volume served by the agent. We have this is going to be the total queries that are served by the market. This is the agent's revenue. You want to see it going up and to the right over time. And this is the aggregated revenue, the total, the aggregated agent revenue. So here is a video showing the agent learning. You can see that it is learning. It's exploring and adjusting to the right until it finds the clearing price. And then you can see its policy gets narrower and narrower, and until it can try to get just up to the price of what the budget is. We've moved this into production. So this is deployed. It's also open source. It's available to be used by all indexers. And here you can see that this is tracking it in production. We can see that the mean of the policy is going up. That means it's finding the price that can maximize its revenue. Its variance goes down. That means it's uncertainty about where its maximum price is. And here we can see that the rewards that it's getting over time goes up. So I appreciate you guys being here today. If you'd like to see a full version of this talk, we presented at DevCon in October. This QR code will link you to a YouTube video. If you'd like to reach out to me, you can email me at sam@semiotic.ai, and my Twitter is 0xsamgreen.
Cool. Awesome. And right on time, it's 1740. So,
That's my goal.
yeah, that means we have 5 minutes to take some questions, and we do have some already. So,
Okay.
yeah, Levy asks, did the mean of the distribution match the max price the customer was willing to pay in the end, or was it a bit lower to increase the probability of a match?
Oh yeah, good question. It's a little bit lower because the variance is never going to go to zero, uh, and yeah. So during that simulation, it goes a little bit lower. In practice, what is happening in a multi-agent? In practice, we have a multi-agent situation with the data sellers, with the indexers. Uh, and so what ends up happening in practice is you get these policies that are wider because there is basically the competition between the agents causes there to need to be ends up there just needs to be a wider distribution so they don't get to maximize the revenue if they don't get right up to that border if they're competing.
Cool. Okay, so there's another one. This is from Michelle. Michelle asks, in the past, we've been trying to do decentralized Uber or ride sharing, and one of the hardest things to solve was to calculate the price for a ride. Could you talk about how this could be used for this?
Yeah, so let's see. Um, Michelle, is this so you could imagine like uh, I mean in general, I think these sorts of solutions, these bandit solutions are very extremely popular for this sort of application. There is a lot of previous work in this domain, and I'd say in general they're a nice solution to try if you're trying to bid for something and you don't know what the price is, that it's going to clear, that's going to win the bid, and if the bid price is changing all of the time, like if the optimal price to bid is changing all the time, these are good solutions. If the price is changing, if it's jumping around like super erratically, this solution, I mean, it'll still work, but it becomes harder. If the price that you need to bid shifts gradually, given like, let's say fluctuations in demand, then I think these are good approaches to try.
Interesting. Okay, I have another one for you. So another one from Levy. What challenges did you face when transitioning from agents trained in simulation to agents in production? Great question.
Yeah, that's a great question. In production, of course, you have the simulation to reality gap, and that's what this question's about. Um, we uh, let's see. So in practice, it's difficult, or in simulation, it's difficult to capture the fluctuations in market demand. Uh, and so, what ended up happening? I'll give you the most interesting lesson. What ended up happening is we deployed this on a we deployed this in a for a subgraph, which is basically like a little marketplace that ended up having no queries, and our agent didn't know that there's like nothing to be had at all. And so what happened is that the policy got so wide, the variance got so wide because it didn't know what to do, and so it became so wide that the policy basically exploded because it didn't know what to price to converge on because there were no offers that were even available. So that was an interesting challenge.
All right. Okay. So it looks like that's the end of our text questions. Is there anything that you didn't get to mention? Maybe you could talk a little bit about how people could connect with you if they want to experiment with this stuff themselves or just learn more.
Yeah, I think Twitter is the best place. 0x Sam Green, and we have open source repos for this. And in general, I'm interested in other applications of using RL for bidding agents in Web3 in particular. So if you're working on anything similar and you just want to chat about these topics, I'd be happy to chat.